Section 4.5, we're going to see how L'Hopital's rule can be used to help us evaluate limits of expressions. The expressions that we're talking about are going to be rational expressions. And we're looking at limits of rational expressions that will have the form 0 over 0 or infinity over infinity. Remember back in chapter 2, when we took some of these limits, we did a lot of algebra. We had to do some factoring. Maybe some problems were hard to factor, so we did some long division, or we used trig identities, things like that. Hopefully, L'Hopital's rule will make these things a little bit easier. So here's the statement of L'Hopital's rule. If f and g are differentiable functions with the limits as of the ratio, x goes to a could be infinity, as x goes to a or x goes to infinity, of the expression f of x over g of x takes on the form 0 over 0, then you can evaluate that limit by taking the limit of the ratio of the derivatives. The reason that works is, remember the linearization of functions? Essentially, we can write the equation of a tangent line. Near x is equal to a, we have that f of x is roughly equal to f of a plus f prime at a times x minus a. So we can do the same thing for g. It's g of a plus g prime of a times x minus a. So if we set up the ratio of f divided by g, we have something like that. Now the reason that the form f over g is indeterminate at x is equal to a is probably because f and g are 0 when x is a. So let's make that supposition. Let's suppose f of a is 0 and g of a is 0. That means in this expression down here, these two guys are zeros, and so they're gone. And that leaves a common factor here of x minus a that we can cancel. So that says that f of x over g of x is roughly equal to f prime of a over g prime of a. In particular, the limit as x goes to a of f of x over g of x squeezes us right to the limit. I need a limit over here. Let's get the limit in there. The limit as x goes to a of f prime at a over g prime at a. So it works because of this linearization property. Now, pay attention to what you're doing. I'm not telling you to take the derivative using the quotient rule. This is the derivative of the top divided by the derivative of the bottom. If you can remember that, L'Hopital's rule is nice and easy and helpful. This is not the quotient rule. So let's look at a boatload of examples, shall we? This is one of the special limits. Remember that the sign of mx divided by n times x as x goes to 0 is one of the ones I asked you to memorize. Sine of 0 is 0 and n times 0 is 0. So this does have the form of 0 over 0. And I said, well, this will always give you m over n. You'll just have to believe me. But let's show you that that's going to work here with L'Hopital's rule. So if I try to take this limit by putting 0 in for each x, I get sine of 0 over 0 or 0 over 0. So I make a note saying that I've got the right form for L'Hopital's rule. So now I'm going to take the derivative of the sine of 3x and get 3 times the cosine of 3x. And then I'm going to take the derivative of 2x and get 2. Now I take the limit, put a 0 in here. Cosine of 0 is 1, so I have 3 times 1 over 2, and there's the 3 halves that I said you'd get by using that theorem. Okay, so it's nice, it works. Now the second example, Remember we had to do something like this. We got 0 over 0 and we had to factor, and I said, oh gosh, I don't remember the factoring rules for x cubed minus 8, and I certainly don't remember the factoring rule for x to the 5th minus 32. But I would suppose there's a factor of x minus 2 in there, and we did long division or synthetic division. Well, with L'Hopital's rule, we don't have to. Make a quick check that when you put 0 in for each x, 2 in for each x, you get 0 over 0. And we do, because 2 to the 5th is 32 and 2 cubed is 8. So what L'Hopital's rule says, take the derivative of the top, and I'll get 5x to the 4th. Take the derivative of the bottom and get 3x squared. Now let's simplify. I can cancel an x squared from the numerator and the denominator, and that leaves me 5x squared over 3. Now when I take the limit by putting 2 in for x, we get 4 times 5 is 20 over 3 is our limit. L'Hopital's rule also works when we take limits to infinity. In the last section, we took this limit to infinity by recognizing the pattern that if I were to divide numerator and denominator by the highest power of x and simplify, in a case where the degree on top is equal to the degree on the bottom, then the limit to infinity should just give us the ratio of the coefficients of the highest powers of x. So we should get 2/4 out of this. I'm going to get that same limit by using L'Hopital's rule. So numerator and denominators are functions of x. X's are going to infinity, so it has the indeterminate form of infinity over infinity. We take the derivative of the top, divide it by the derivative of the bottom. On top, my derivative is 4x plus 3. On bottom, my derivative is 8x plus 5. Both numerator and denominator have an x in them, so they still go to infinity. So it still has that indeterminate form. So we can use L'Hopital's rule again. Take the derivative of the top, divide it by the derivative of the bottom, and shabam. That's where we get the 1/2 that we would have gotten just by looking at the ratio of the coefficients. There are other indeterminate forms. Infinity times 0 and infinity minus infinity are the two indeterminate forms that we can use algebra for. And we're going to use algebra to get this in the form of 0 over 0 or infinity over infinity. So in the first example, when x goes to infinity, I have infinity times e to the minus infinity. But e to the minus infinity is the same as 1 over e to the infinity, so it's infinity times 0. So this is the 0 that we need to fix, and we can fix it just by taking the term with the negative power, writing it in the denominator with a positive power. And now I have the form of infinity over infinity. Not much algebra, but there you go. We got it in the right form for L'Hopital's rule. Let's take the derivative of the top, divide it by the derivative of the bottom. There's the derivative of the top over the bottom. Now I let x go to infinity, and so I get 1 over infinity, and my limit is 0. In my next example, x is going to 0 from the right. We take x from the right because remember the logarithm is only defined for positive x's. In fact, as I'm coming in from the right, the logarithm is going to minus infinity. The x is going to 0. So 0 times infinity, 0 times minus infinity, that's still the same type of indeterminate form. I want to put it in the form of either 0 over 0 or infinity over infinity. And here, my trick is to note that multiplying by x is the same as dividing by 1 over x. Right? When you divide by 1 over x, you flip and multiply, and that would give us the original expression. But now I have the form of infinity over infinity, since 1 over 0 becomes infinitely large. So we do L'Hopital's rule. We take the derivative of the top and divide it by the derivative of the bottom. The derivative of the natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Now we simplify. I'll have 1 over x times negative x squared over 1. The x's will cancel, and it leaves me the limit as x goes to 0 of minus x. X is going to 0, so again I get a limit of 0. Okay, now remember things like the next one. We had these examples back in chapter 2, and I bet you remember what to do. We'll probably have to do that again, because as x goes to infinity, we have infinity minus infinity. What we did in chapter 2 is we made this into a fraction by multiplying by the conjugate. The conjugate is going to look like x squared minus x, and then put a plus sign here. Put a plus sign between the radical term and the non-radical term. Now that's going to give me a single fraction. When I multiply the two radicals together, I'm going to get x squared minus x. The inside terms, this times this and that times that, give us the same product but opposite in sign. So those are going to add out. And then finally the product of the minus x with the plus x gives me a minus x squared. And then we have the square root of x squared minus x plus x. So we have the limit as x goes to infinity of minus x over the square root of x squared plus x. Oops, sorry, that should be a minus x. Minus x here, and the square root of x squared minus x plus x. Now, unfortunately, this is at the bottom of my page. What I wanted to show you was L'Hopital's rule works very poorly for expressions that have radicals in them. I guess I've got a little bit of room here. I'll show you that L'Hopital's rule is not good for expressions like this. I mean, I can try it, but I'm going to get a mess. So we're going to take the derivative of the top and divide it by the derivative of the bottom. The derivative of the top is easy enough. That's a negative 1. The derivative of the bottom, remember that a radical sign is a half power. So I'm going to get 1/2 x squared minus x to the negative 1/2 plus 1. I'll need to simplify that. Oops, I left out the derivative of the inside, and you guys let me do that. Let's go back here and fix that. We've got to multiply by the derivative of what's inside. We're going to get a 2x here. Then the derivative of the x gives me the plus 1. Okay, so to simplify this first term, I'm going to take this 1/2 and multiply it with the 2x and just get an x. And then I'm going to write the x squared minus x to the 1/2 on the bottom. So take a look at what's happened. I've got x going to infinity, and this expression here in the denominator has the form of infinity over infinity. So that's bad. I can try to clean that up by multiplying top and bottom by this denominator, x squared minus x to the 1/2 over x squared minus x to the 1/2. But then we get something that almost looks like what we started with, right? When I multiply out the top, I get that. When I multiply out the bottom, this one would cancel, leave me an x, but then here I get that radical back. So by gosh, we're at infinity over infinity. And guess what happens if we try L'Hopital's rule again? When we take the derivative of this expression here, it's going to have a negative 1/2 power, which puts it in the denominator. When I take the derivative of this thing here, it's going to have a negative power, which will eventually put that back in the numerator. So I'm going to keep flip-flopping this expression. I'll always have a radical in it. So I'll never be able to get it out of infinity over infinity form. Okay, so we're stuck. We are in an infinite loop of infinity over infinity. So that's why I say L'Hopital's rule is not going to be good for stuff with radicals. So let's go back to the expression that I have circled and see if we can evaluate this limit the way we did in the last section. So whip out my eraser. Let's rub all this stuff out because it didn't work. And let's go back here and look at how we would do that with the last section. With the last section, we looked at the degree on top. The highest degree on top is x to the first power. The degree on the bottom, good gosh, can't spell degree. The degree on the bottom, I've got a square root of x squared, and I've got an x to the first power as well. So if we were to look at the ratio of the coefficients of the highest powers of x, right? It's going to give that our limit is equal to, let's see, I've got a minus x here, a square root of x squared here, that minus x is a lesser term, and that x. So the coefficients I'm looking at are here, here, and here. And so we get a negative 1 on top, a square root of 1 on the bottom, and then that 1. But the square root of 1 is 1, so I get my limit is negative 1/2. Okay, so be careful using L'Hopital's rule with radical signs. Sometimes we just have to use our ratio of coefficients rules. Now we'll look at the exponential indeterminate forms, 1 to the infinity, 0 to the 0, and infinity to the 0. We can take them out of those exponential forms using a logarithm, because remember that the log of anything to a power can be written as that power times the log of anything. And so when we encounter these rules, we're going to use a logarithm. All right, in my first example, 1 plus 1 over x all to the x. As x goes to infinity, 1 over x goes to 0. So the stuff in the parentheses acts like 1. And then the x is going to infinity. So it's that first indeterminate form, 1 to the infinity. I'm going to pretend that this thing has a limit, and I'm going to call it L. And now I'm going to take the natural log of both sides, and I'm going to move the natural log into the limit. So write the limit first. Put the natural log right here. And now I'm going to take the natural log of the other side. Next, I'm going to use that property of logarithms that puts the exponent down in front. So I have the limit as x goes to infinity of x times the natural log of 1 plus 1 over x is equal to the natural log of L. So now it's out of the exponential form, but the form that it is currently in is this x is going to infinity. This fraction goes to 0. 1 over infinity goes to 0. Natural log of 1 is 0. So we have the infinity times 0 rule. We're going to handle that the way we did before when we had x times the log of x. We took the x in the front, put its reciprocal in the denominator. Dividing by 1 over x is equivalent to multiplying by x. But now I have 0 over 0. Natural log of 1 plus 1 over infinity. 1 over infinity is going to go to 0. So the natural log of 1 is 0. 1 over infinity is 0. Now we're going to use L'Hopital's rule. Take the derivative of the top. The top is a logarithm. So the derivative log of u is 1 over u times the derivative of u. So I'm going inside here. The derivative of the 1 is 0. The derivative of 1 over x is negative 1 over x squared. Now we're going downstairs and we're going to take the derivative of the 1 over x there, and again we get a negative 1 over x squared. Those factors cancel right there. And so I'm just taking the limit of the inside expression. Let's bring it up here. We're almost done. I've got the limit as x goes to infinity of 1 over 1 plus 1 over x. And remember, that's the natural log of the limit. X is going to infinity, so this little guy out here goes to 0. And I get that 1 is equal to the natural log of L. Right? Now to get L, we exponentiate both sides. So our limit is e. This is roughly the definition of e. 1 plus 1 over n to the n as n goes to infinity. So when you see something like that, you kind of suspect you're going to get e to some sort of power. I think we've got time for one more here. Let's look at the limit as x goes to 0 from the right of x sine of x. So this one has the form 0 to the 0 power, since the sine of 0 is 0. So we start the exact same way. Pretend there's a limit, call it L. Take the natural log of both sides. We're going to squeeze the natural log in here. And keep the natural log of L over here. Now we use the log property. That puts a sine of x in front here and a natural log of x here. Now, as x goes to 0, sine of 0 is 0, but the log near 0 is infinite. It's actually minus infinity. But it's got the indeterminate form of 0 times infinity, just like we had up here in the earlier example. So we pick one of the terms and put its reciprocal in the denominator. I'm going to put the reciprocal of the sine in the denominator. Let's leave the logarithm on top and put 1 over sine down here. I've used the sine to put its reciprocal down there because we have all that trig. We have a trig identity for that. 1 over sine is the cosecant. So I'm going to write this as the natural log of x over the cosecant of x. Now, as x goes to 0, the logarithm still gets infinitely large, and the cosecant also goes to infinity because it's acting like 1 over 0. Now I have the right format for L'Hopital's rule. And so we take the derivative of the top and divide it by the derivative of the bottom. Derivative of the top gives me 1 over x. Hope you remember your derivative of the cosecant. Starts with a c, so I know there's a minus. And it looks like the same format as the derivative of the secant. It's going to have a minus cosecant of x and a cotangent of x. Let's bring it up here and simplify. Now, let's do some trig. I'm going to have the 1 over x up here. Cosecant is 1 over the sine. Cotangent is the cosine over the sine. So I have this. Remember that that's all still equal to the natural log of L. I just don't have room to write that anymore. I have 1 over x over a negative cosine of x over the sine squared of x. So we're going to have to flip and multiply. So I'm going to have a 1 over x sine squared of x over a negative cosine of x. Let me go ahead and put the negative here. In fact, I can make that all one fraction. But look, as x goes to 0, sine of 0 is 0, and I've got a 0 down here. So I've got the form of 0 divided by 0. We're going to need to do L'Hopital's rule again. So I've got to scroll to another page. We've got sine squared over x cosine of x. Right? Let me make a quick look. Yes, minus sine squared over x cosine of x. But we decided that that was 0 over 0, so we can do L'Hopital's rule. But remember, that's equal to the natural log of L from way back here. So let's be careful. Now we're going to do L'Hopital's rule. Derivative of sine squared using the power rule. Bring the power down, raise the function to 1 power less, then multiply by the derivative inside. Downstairs, we've got to do the product rule. It's the first times the derivative of the second plus the second times the derivative of the first. Now we're going to let x go to 0. As x goes to 0, this term is 0. This term is 1. So on top I get negative 2 times 0 times 1 is 0. On bottom, this is 0, but this is 1. So I have 0 over 0 plus 1. That's no longer indeterminate. That's 0. So I have 0 is equal to the natural log of L. And then we get rid of the natural log of L by exponentiating both sides. E to the 0 is 1. 1 is equal to L. There are all of my examples for L'Hopital's rule. Try reading over the notes and trying your web work problems, and then we'll talk about these in our virtual